Hello everyone, I am Dr. Rizwana, working as a Professor of Physics in Institute of Aeronautical Engineering. Today in our video, I am going to discuss about carrier concentration in intrinsic semiconductors. So in my last video, we have discussed in detail about intrinsic semiconductors. Now today what we'll try to do here is in intrinsic semiconductors, as we know that we have two types of charge carriers, electrons and holes, and these electrons and holes, they are equal in number. So we'll try to get expression for electron concentration as well as the hole concentration in intrinsic semiconductors, and also using this expression for electrons and holes, we'll try to get expression for intrinsic carrier concentration. So we'll proceed further with our video. As I told you, we are going to get expression for electron and hole concentration in intrinsic semiconductors. Quickly we'll try to recollect what are intrinsic semiconductors. So this is the figure for intrinsic semiconductor. We know that a semiconductor, it's a material whose electrical properties are between conductors and insulators. And what you will observe here is these best examples for these semiconductors are silicon and germanium, and basically they are insulators, and we can make them conductors by supplying energy because their forbidden energy gap is small. So with the supply of suitable form of energy, we can make them conductors. Now coming to intrinsic semiconductors, they are pure semiconductors. So we'll take either silicon crystal or germanium crystal. And germanium crystal, it is made up of germanium atoms. Silicon crystal, it is made up of silicon atoms. So here we are not going to add any foreign atom. Okay. So here we don't have any impurity or dopants being added to intrinsic semiconductor. It's a pure semiconductor. And we are going to study its behavior at normal temperature and also at temperatures when we take them to very high temperatures. Now in this figure, as you can see, we have taken silicon crystal, which consists of many silicon atoms. And here we know that silicon and germanium, they belong to group 4. And it means that silicon and germanium, they consist of 4 valence electrons. So they belong to group 4, silicon and germanium, and they consist of 4 valence electrons. And if you take each silicon atom, these 4 valence electrons, they will form 4 covalent bonds with adjacent silicon atoms in order to attain octet configuration. And because electrons, they are taking part in bond formation, there are no free electrons. So that's why we'll say that intrinsic semiconductors are insulators at T is equal to 0 Kelvin. So they are insulators at T is equal to 0 kelvins. Now if you see this energy band diagram, here valence band is completely filled. What you will observe here is valence band, which is consists of series of energy levels which are occupied by valence electrons, and here valence band is completely filled. And because number of valence electrons are more, they are very strongly attracted towards the nucleus. So that's why there won't be any electrons in the conduction band. Our conduction band will be vacant at normal temperature, whereas valence band will be completely filled. So there are no free electrons, as all electrons are taking part in covalent bond formation. That's why they behave as insulator. Whereas if we increase temperature, what we observe here is now covalent bonds will break. What do you mean by covalent bond breaking? It means that electrons, they will come out of their bound state and they will be in free state. They will be freely flowing from one place to other place. So if you see this energy band diagram, first our electrons, they were present in valence band. When we go to high temperature, these electrons, they will start jumping from valence band to conduction band. And once electrons jump from valence band to conduction band, we will have holes in valence band and electrons in conduction band. So you will have plenty of free electrons in conduction band, which will make it conductor. So here all the bonds will break, and then we will have lot of free electrons which will contribute to electrical conductivity. And one very important point what we have to observe in case of intrinsic semiconductors is, here what we'll observe here is, if we take these intrinsic semiconductors, if one electron takes transition from valence band to conduction band, then that electron vacant site in valence band, that is nothing but hole, and one free electron in conduction band. So whenever there is one transition from valence band to conduction band, then one free hole in valence band and one free electron in conduction band will be produced. So depending upon how many transitions are taking place, based on that we'll have so many number of electron hole pairs. So we'll observe that only in intrinsic semiconductors we'll have equal number of electrons and holes both in conduction band and valence band respectively. So that's why when we are trying to find carrier concentration in intrinsic semiconductors, so what do you mean by carrier concentration? How many number of charge carriers are present per unit volume of the material, or intrinsic semiconductor is nothing but carrier concentration. So number of charge carriers present per unit volume in an intrinsic semiconductor is nothing but carrier concentration. And in intrinsic semiconductors, number of holes in valence band will be equal to number of electrons in the conduction band. So that's why we have to get expression for number of electrons in the conduction band, or density of electrons in conduction band, or number of holes per unit volume in the valence band. So we are going to calculate number of electrons per unit volume in conduction band, number of holes per unit volume in the valence band. So in our next slides, we are going to derive expression for both electron and hole concentration. First, we are going to start with electron concentration in intrinsic semiconductors. As I told you, what do you mean by concentration? Because here we are talking about electron concentration. How many number of electrons are present in the conduction band? And concentration means number of charge carriers per unit volume. So number of free electrons per unit volume of conduction band of a given intrinsic semiconductor is called electron concentration. Because we are finding electron concentration, so what is our charge carrier right now we are considering? We are considering electron. So how many number of free electrons are present per unit volume in the conduction band will give us electron concentration, and it is represented by N, notation N. And why we are using N? Because electrons are negatively charged, that's why we have taken N. And in case of the holes, because holes are positively charged, we will make use of notation P. So now we'll start our derivation. So as we know that if we take our energy band diagram, so if we take our energy band diagram, we have lower band. That lower band is nothing but our valence band. So this is our valence band. And then we have our higher permitted band, that is nothing but conduction band. So here we have conduction band. And here what we are going to do, here we'll take bottommost energy level of conduction band. Bottommost energy level of conduction band will take it as EC, whereas topmost of valence band will take it as EV. Okay, and you will observe that whether it is valence band or conduction band, they consist of so many number of energy levels or energy states. So now we are finding electron concentration. So electron concentration means how many number of electrons are present per unit volume. So here what I am going to do here is, instead of finding total number of free electrons in entire conduction band, so what I'll do here is, here I'll set, again I'm going to draw this energy level diagram. So we are going to concentrate on conduction band. Now this conduction band, it is made up of continuous energy levels. It consists of continuous energy states, and EC defines bottom energy level of conduction band. Now what I am going to do, first, instead of finding total number of free electrons in all these energy levels, what I am going to do, I am going to select set of energy levels. Okay, and that energy levels I am calling them as DE. So I'm going to select certain set of energy levels. I'm going to select small energy interval, and that energy interval it is called as T. Suppose if this is taken as E, then this it is taken as E plus D. So we are considering So this is taken as E plus D. So we are considering small energy interval D. It means that we are considering small set of energy levels in conduction band. We'll try to find how many number of electrons are present in that small energy interval, and then we'll try to find total number of free electrons in entire conduction band. So what I have done in my first case, let us suppose that number of free electrons per unit volume. It means that I'm talking about density of electrons. So number of electrons per unit volume, it is also called as density of electrons. So density of electrons in the conduction band in the energy interval E and E plus D, that is nothing but D. And how it is represented? N of E dE. So N representation is for total number of electrons in entire conduction band. But here we are considering small energy interval D. So that number of electrons in the small energy interval D, I am denoting it by N of E dE. And this N of E d, it consists of two terms. Now how it is given? It is given as made up of two terms. As you can see, first one is Z of E dE and second one is F of E, and of course both will represent with respect to conduction band. Now what is Z of E dE? Now Z of E dE, it is called as density of energy states. So what do you mean by density of energy states? Density of energy state is nothing but how many number of energy states are present per unit volume in the energy interval dE. Okay, so what is the first term that I am using in order to get expression for density of electrons in small energy interval dE? First term is I am taking how many number of energy states are present per unit volume in the small energy interval dE into F of E. What is F of E? F of E, it is called as Fermi-Dirac distribution function. So what do you mean by Fermi-Dirac distribution function? This function, it will give you what is the probability of an electron occupying a particular energy state is nothing but Fermi-Dirac distribution function. So here, what you will observe here is, because I have taken conduction band, in this conduction band, I have taken a set of energy interval dE. Now, first, in order to know how many number of electrons, I should know how many number of energy states are available in that energy interval. And the next thing is, what is the probability? So, what are the chances of an electron going and sitting, going or jumping to that particular energy state? That probability also have to consider. So that's why, suppose I have around 5 number of energy states, and in that 5 number of energy state I am able to accommodate 10 electrons. So that 5 number of energy states into how many number of electrons I am able to accommodate will give us how many number of electrons are present in the energy interval D. So this is our first expression for derivation of carrier concentration. So what we have learned here is, in order to find density of electrons or number of electrons per unit volume in an energy interval dE, it means that we are selecting small set of energy states. In that small set of energy states, we are calling it as dE, and that in order to find, we are taking two terms. In that first term is density of energy states in that particular energy interval dE, and then what is the probability of an electron going and sitting in particular energy state is given by Fermi-Dirac distribution function. And why we have to take care of Fermi-Dirac distribution function? Because electron occupancy, it is given by Pauli's exclusion principle. And according to Pauli's exclusion principle, here not more than 2 electrons per energy state. So it means that we cannot go and dump electrons in all energy states. So there is a rule for occupation of the electron. And what are the chances when you supply energy? What are the chances of electron going to that particular energy level? It will be taken care of this Fermi-Dirac distribution function. Now we are going to get expression for density of energy states as well as Fermi-Dirac distribution function, and we are going to substitute. First, I am trying to get expression for density of energy states. Now density of energy states in conduction band, it is given as, now we cannot separate this Z of E dE. This is the entire notation. Total, it will denote density of energy states. And what is the formula given? So we are taking this formula as it is. pi by 2 into 8 me star by h square whole to the power of 3 by 2 into e to the power of half d. So this is the expression for density of energy states. And as you can make out, what is me star? Me star is effective mass of an electron. And what do we mean by effective mass of an electron? See, in our previous videos, we have discussed about band theory of solids. In that band theory of solids, we have discussed about periodic potential. So our electron, it is moving in a periodic potential. When we have such electron moving in a periodic potential, what you will observe here is mass of electron, it is going to vary with velocity. Mass varies with velocity. And when mass varies with velocity, when electron in a periodic potential, is accelerated. And how it is accelerated? It is accelerated either by applying electric field or magnetic field. So when we have electron moving in a periodic potential, and if it is accelerated by electric or magnetic field, then its mass varies with velocity. So such particular mass, it is known as effective mass of an electron. So me star is effective mass of electron. What is h? H is nothing but our Planck's constant and whole to the power of 3 by 2, and we are talking about a particular energy state, and here particular energy state in energy interval d. So in this energy interval d, we are going to consider any one of the particular energy state. So this is the expression for density of energy states. Now we should try to get expression for Fermi-Dirac distribution function. Now what we have done here is, here as you can see, this is very, very important. Now I have taken conduction band, and in conduction band we have series of energy levels. So this is our series of energy levels, as you can make out. Okay, and what is the bottom of conduction band? Bottom of conduction band, it is given by EC. So EC denotes bottom of conduction band. Now I have considered, so in this case I have considered set of energy levels, and that energy interval I am calling it as D. So that energy interval we are calling it as D. Now what you are observing here is, it means that I am considering that DE above EC. So I am considering energy levels above EC. I am not considering energy levels below EC. So that's why what you will observe here is, as whatever energy level we are taking, any energy level we are taking, it is present above EC. What is EC? EC is bottommost energy level of the conduction band. So as you can see in our equation 2 which we have taken, in place of E, I'll take E minus EC. So in place of E, I'm going to take E minus EC. Why I'm taking E minus EC? In order to show that I'm considering energy levels. So here we are considering energy levels above EC. So we are considering energy levels above EC. So that's why in place of E, we are taking E minus EC. So this is the final expression for density of energy states in the energy interval D. Then coming to Fermi-Dirac distribution function. An expression for Fermi-Dirac distribution function in conduction band, formula it is given by 1 plus exponential E minus EF by kBT. So what is EF? I think already we have discussed about EF in our previous video where we have taken introduction about semiconductors. EF is nothing but the Fermi level. And what is Fermi level? As I told you, this Fermi level location, see Fermi level, it is one of the energy level, and location of this energy level, it is going to be different at different temperatures. And I told you that at T is equal to 0 kelvins, Fermi energy level, it is defined as the boundary energy level, which is going to separate filled energy states and unfilled energy states. Suppose I have one band. In that band, I have filled energy levels occupied by electrons, and then I have unfilled energy levels. So these are unfilled energy levels, and whereas these are filled energy levels. So these are filled energy levels. Now I'll have one boundary energy level. That boundary energy level, it is called as EF, which is separating filled states and unfilled states, and that this definition is suitable at T is equal to 0 kelvins. Like this, if you go to higher temperature, we can define Fermi energy level as the Fermi energy level where electron occupation is half. There is half probability of occupation of electrons. So like this Fermi energy level location, it is going to change based on temperature and also based on material. And what we'll observe here is in future slides or future videos, we'll see what is the location of Fermi level in intrinsic semiconductors as well as what is the location of Fermi level in extrinsic semiconductors. And you'll find that in case of intrinsic semiconductors, Fermi level is exactly at the middle of conduction band and valence band, or it is exactly at the middle of forbidden energy gap. So that we are going to derive and we are going to discuss about it later, but for the time being, we are saying it's one of the energy level. In terms of this Fermi energy level, Fermi-Dirac distribution function, it is given by this formula. And what is Kb? Kb, it is Boltzmann constant. So Kb, it is given as Boltzmann constant, which is 1.38 into 10 power of minus 23 joule per Kelvin. And of course, T is the temperature at which we are trying to find what is the probability of occupation of electron for one particular energy, E. Now, we'll try to simplify this Fermi-Dirac distribution function. So when we are trying to simplify this Fermi-Dirac distribution function, now, if you take this formula, usually what you will observe here is our energy level will be greater than EF. So this E, always E, whatever energy level we are considering, it will be always greater than Fermi energy level. So what you will observe here is this total term, it will be very much greater than 1. So this value, it will be very much greater than 1. Hence, we can neglect 1 in this equation just for simplicity's sake. And if we neglect this 1, then we are left with only 1 divided by, in the denominator we will have only exponential term, which is E minus EF by kBt. And we know that 1 by E is nothing but e to the power of minus 1, or 1 by e to the power of a is e to the power of minus a. So if this exponential goes up, instead of e minus ef, we'll have ef minus e by kBt. So this is the simplified formula for Fermi-Dirac distribution function when we are considering electrons in conduction band. So next, what we are going to do, this final expression for density of energy states given by equation 3 and Fermi-Dirac distribution function, which is given by equation 5, we are going to substitute in our first equation this equation where we are trying to find density of electrons in energy interval dE in the conduction band. So here we are going to substitute density of energy states as well as Fermi-Dirac distribution function. So when we substitute those formulas, what you will observe here is, so N of E dE, so here you will observe that in this case N of E dE, so it is given as pi by 2. This is the expression for, if you take this is the expression for density of energy states. This is the expression for density of energy states which we have copied from our previous equation 3, and this is the expression for equation 4. This came from equation 4 and this came from equation 3. And if we try to simplify it, so we have taken our dE outside. Now what is N of E dE? So N of E dE, it is the density of electrons in a small energy interval which we are considering in the conduction band. So we have taken only dE. Suppose if I want to find density of electrons in entire conduction band. So if you want to find density of electrons in entire conduction band, then what I have to do, I have to integrate this equation. What is this equation? Density of electron in small energy interval dE. Now tell me what can be the limits of integration. What is the bottom energy level in case of conduction band? So it is given by EC. And what is the top energy level of conduction band, which is undefined. So that's why we'll take it to be infinity. So bottom energy level of conduction band is EC, whereas topmost energy level is, we are considering it to be infinity. So if we integrate this equation 6 between the limits EC to infinity, then we'll get total number of electrons in entire conduction band, which is represented by N. So in entire conduction band, it is represented by N. N EC to infinity pi by 2, 8 pi me star by h square whole to the power of 3 by 2, E minus EC whole to the power of half, exponential EF minus E by kBt d. Now if you take this expression, we'll try to take constant terms outside the integral. Now this term pi by 2, 8 mv star by h square whole to the power of 3 by 2 is constant, and here our EF is also constant. So here first we'll try to remove this pi by 2, 8 mv star by h square whole to the power of 3 by 2. We'll take it outside. When we have taken it outside, then what we have in integration, EC to infinity E minus EC whole to the power of half, exponential EF minus E by kBt t. Okay, so now what I'm doing here is, I think it is not easy to integrate it. It's a complicated one. So that's why we'll try to simplify it. In order to simplify it, what I'm doing here is, I'm introducing one factor epsilon, and that epsilon I'm taking it as E minus EC. So I'm defining E minus EC just for simplicity's sake as epsilon. And if we differentiate it, d epsilon is equal to dE because EC is constant. So EF, EC, EV, all these are constant energy values. So here d epsilon is equal to dE as EC is our constant. Now limits will also change. Instead of EC to infinity, suppose if I substitute lower limit EC in place of E, I'll have my epsilon to be 0, because our epsilon is E minus EC. When our E is equal to EC, then we'll have our epsilon as EC minus EC. This is equal to 0. Okay, whereas if I take my E to be infinity, then epsilon will be infinity minus EC, which will be equal to infinity. So that's why our limits, they will change from 0 to infinity. So what happens to our equation? Now limits will be from 0 to infinity, and in place of E minus EC, we have our epsilon. And here from this, what is our E? If you take this expression, from this we have our E as epsilon plus EC. So it is epsilon plus EC. And here if you see, EF and EC both are constants. So I'm taking out this EF and EC outside the integral. Then I'll have EF minus EC by kBt coming outside the integral. So what is left now? Now integration 0 to infinity, epsilon whole to the power of half, exponential minus epsilon by kBt d epsilon. Now what is this? This is nothing but gamma integral. This is called as gamma integral. So this particular thing, it is called as gamma integral. And what is the value? There is one standard value for this gamma integral. So this gamma integral, it is given by this formula. So where we have is, what is the value of this gamma integral? Pi to the power of half by 2 into kBt whole to the power of 3 by 2. This is the standard gamma integral value. We are going to substitute that value in our previous equation 8. Then what I am doing here is, I am trying to simplify all those terms. I am taking all the terms with power 3 by 2 to one side. Then here I'll have, see here, 2 into 2, 4 will be there. Pi whole to the power of 3 by 2. T whole to the power of 3 by 2, KB whole to the power of 3 by 2, and then 8 me star by h square also whole to the power of 3 by 2. So I'm getting all those terms together and I'm taking their power to be 3 by 2. So exponential EF minus EC by kBt. So now if I take this, so what I'm doing here is, I have 8, and this 8, it can be written as 4 into 2. So 4 into 2 whole to the power of 3 by 2. I can write it as, here 4 is 2 square whole to the power of 3 by 2 into 2 to the power of 3 by 2. So here you'll be left with 2 to the power of 3 by 2, and this 2 cube will be 8. So 8 by 4 will be 2. So this is the final expression for electron concentration in conduction band. So 2 into 2 pi me star kBt by h square whole to the power of 3 by 2 exponential EF minus EC by kBt, where EF is Fermi energy level and EC is bottommost of conduction band. So finally we are able to get expression for density of electrons in the entire conduction band. So today we have taken introduction about intrinsic semiconductors, and we know that in intrinsic semiconductors we have number of holes or density of holes in the valence band and density of electrons in the conduction band, both of them are equal. So we are trying to get expression for electron concentration as well as hole concentration. Today in this video we are going to we have finished how to derive expression for the electron concentration. So in my next video you are going to see derivation for concentration of holes in the valence band. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.